minute. Yeah. So now we want to look at the cell cycle, because as we have said, most of these drugs want to attack the mitosis when these cells are dividing. So one needs to understand the cell cycle so that they can understand the activity of these drugs. Of course, when we classify these drugs, we can classify them according to their structures. Of course, the structure is not very definite. It's usually structure combined with mode of action, but we can also classify them, especially in pharmacology, according to the stage or according to the phase, or how psychospecific they are. What stage of the cycle are they affecting? But for us in PharmChem, we look at more on the structure. So we can look at the cell cycle, and we can note the cell cycle is a series of events that takes place in a cell, leading to the duplication of the DNA, division of the cytoplasm and organelles to produce two daughter cells. Remember, you start with one cell, and that one cell must divide to give you two daughter cells. And those two daughter cells must be the same as the original cell. So for you to start with one cell and then it divides to give you two cells, remember, you have the nucleus, which has the chromosomes. It has some also nuclear proteins and so on. So all those must first of all double. It has a DNA. Everything must go into double. Once everything goes into double, and then they separate. Contents of one daughter cell on one side, contents of the other daughter cell on the other side. When that then happens, then the whole cell now divides into two, and you get two young, let's call them young daughter cells, very young daughter cells. And those, they prefer to call them daughter cells. And then those daughter cells must grow because they are young, they will grow. So therefore, they will grow in size. The DNAs will grow, the proteins, they will generate proteins. Perhaps there is some proteins they don't have, like some enzymes which are not fully developed. So they will develop their enzymes, they will develop their structural proteins, and now again, the daughter cell will grow to maturity and it will be a fully grown cell. And then now it can again divide. Or if it does not require to divide, because we have said division of a normal cell is under regulatory control. So if it does not require to continue dividing, then it will go to resting stage and it will rest until it requires to divide. Because sometimes when the body is fully formed, the development of new cells more often than not is for repair. You perhaps a cell has undergone death or apoptosis, it has died, and therefore you need to replace it, or has been injured, you need to replace it. So it's not a lot of division, not as the embryo is growing. Now this time for an adult, it is for replacement, or for if there is a development of a new enzyme. So that is when you will require the cells to divide. So if you do not require any more of those cells, it goes to rest, and then it will be called upon again when it is required. Now we say it when it is cancerous, no regulation. So once it starts dividing, it's already the oncogene starts dividing, triggered, abnormal cell, divide without any control. So that's what we are talking about. So when we look at the normal cell cycle, we are saying it's divided in two major phases. You have the M phase and you have the interphase. The M phase is further divided into two, the mitosis and the cytokinesis. And of course, the mitosis will have the prophase, the prometaphase, the metaphase, the anaphase, and the telophase. And of course, this is when we have mitosis, is when you have the chromosomes dividing. They divide into two and they separate. The cytokinesis is when now the whole cell divide. And then you have the interphase, which mainly is the period between the mitosis, and you have the interphase, where you can have the G1, you can have the gap one, you can have the synthesis, you can have the second gap. And in this one, it's just basically growth and differentiation. that the cell, after the cell has been formed through mitosis and cytokinases, it is a daughter cell. So it must grow and it must undergo differentiation so that it forms the actual cell that you require as per the trigger, the original trigger or the original need. So this indeed is growth and differentiation. And of course, this is where we are calling the division of the cell. So that is the cell cycle. Perhaps you can say something more about it. So it has two major phases, the M phase and interphase. The M phase, it includes mitosis and cytokinases. And when you look at mitosis, in mitosis, the duplicated chromosomes in the nucleus are evenly divided between the cells. So the mitosis, the chromosomes will form doubles and then they'll divide. They are still within the same cell. They'll move to the two extreme ends and, of course, ready now for the cytokinases. The cytokinases, the entire cell divides into two daughter cells. Then the interphase. Within the interphase, of course, the interphase is where we have said, look at our interphase, is where we have said it is the growth and differentiation. Within our interphase, the cell grows and engages in diverse metabolic activities. This is a period between cell divisions in gap 1 or G1 phase or gap 1, so which is the longest phase. Then uniform daughter cells grows. The cell is metabolically active, duplicates its organelles and cytosolic components. In the S phase, synthesis phase, the DNA replication, duplication of the chromosomes. But we can see the first thing is it grows. So it was a daughter cell. It must first grow. It must first grow, and it is old enough. And once now it's old enough, it will start now again preparing. There will be there is its DNA. The DNA will duplicate, or it will replicate rather. This duplicating is also like replicating. So it's metabolically active, meaning it is growing. It is growing a lot, and then the organelles will replicate. The cytosol components will also replicate. There's a synthesis phase. The DNA will replicate, takes place during this phase. The chromosomes will also replicate. And then the entire DNA molecule, as well as the chromatin proteins that's associated, all of them will replicate. Each DNA replicates to form two sister chromatids held at the centromere. So they are held at the center. So they have grown and they have replicated. And now, after all this, so you can see here the chromosomes. Duplication of the chromosomes involve the accurate copying of the chromosomes. Everything has replicated, and they are now ready to go into mitosis, as we've already said. So many nucleotides are synthesized, and during this phase, there is intensive energy. Intensive energy is required. You also have the GAP2 enzyme and protein synthesis occurs. ATP is produced in large amounts, and centriole replicates. G2 phase ends when mitosis begins. So, in other words, this interphase is like preparation. The cell is preparing for mitosis because it did not go to GO to rest. It didn't quit the cell cycle. If it decided to quit the cell cycle, it will just rest. But it's continuing with the cell cycle. It's preparing to undergo mitosis. So everything is replicating, preparing to undergo mitosis, whereby the chromosomes will separate. So they have replicated. So in this one, we have said they have replicated and they're joined at the two ends, at the centromere. But now when they get in the mitosis, they will separate and go to each pore of the cell, and the cell now is ready to undergo cytokinases and divides into two. So that's what we're calling the cell cycle. And there are some drugs. We have said you can be able to classify the drugs either according to the structure or according to the cell specificity, which area or which cycle. Discussing here, which phase of the cell cycle do they affect? Which phase of the cell cycle do they affect? But for us, we mainly look at the structure of these compounds and the mode of action. So this is what we are saying. So you have here, this is the mitosis on this side, that is the interphase on this side. So you can see we have the daughter cells, which is formed, and it can decide to rest, not to undergo any more cell division. If it goes back into cell division, it's going to G1, and we are saying it's growing. So there will be early protein synthesis, and then there will be DNA synthesis, there will be RNA synthesis. So it is growing. It's growing, preparing to undergo mitosis. And once it is grown, then we have seen there will be also replication of the organelles, replication of the chromosomes, and all that replication. And then after that, it will enter into mitosis, where is the prophase, metaphase, and anaphase, and then the telophase, where you can see the chromosomes have all moved into each pole like this. So these are the chromosomes, those are the chromosomes, and of course the organelles. Each of the organelles which are needed by that cell have moved there. The chromatids, everything has moved to its corner. And then now, after that, is when you have the cytokinase, and when the cytokinase happens, it will give you two daughter cells. And as we have said, it is either to rest again or to continue. I believe, again, as I said that here, most of that is pharmacology, and you will be able to do it in pharmacology. So when you look at classification, it can be based on the site of action, as we have said, the phase in which the drug is acting. It can also be based on the chemical classification, which also includes a mode of action. I've said chemical classification, mode of action, because we realize we mix both of them. These are not like the way we are looking at the antibacterial agents like the penicillins, and we can look at of course, for some of them, we're able to look at, like when we look at penicillins, and all of them are in one class, and they have the same mode of action. These have very many different mode of action. So we can do based on the site of action. And when you can look at based on site of action, we are looking at phase-specific agents, as we have said. Which phase of the cell cycle does this drug affect? We have looked at the mitosis M phase, we have looked at the interphase, we have looked at the mitosis, we have looked at the cytokinase, we have looked at the interphase, where we have said we have the G1, we have the G2, we have the S. Which phase of the cell cycle does the drug affect? And we see the G1, where we have vincristin, we have the S. Remember, the S is the synthesis. This is the area of preparation. You have the S, which is the synthesis. We have the methotrexate, cytarabine. We're going to look at all this. 6, the guanine, 6, mercaptopurine, 5, fluorouracil, daunorubicin, doxorubicin. All those will affect the S phase. Then we have the G2 phase. Again, we have the daunorubicin also can affect the G2 phase, the bleomycin. That's why I thought it was important for us to understand those different phases. Then we have the M phase, which is a mitosis. Again, we can have vincristin, vinblastin, and paclitaxel. By the time we are done, we'll understand the classification of these different drugs. So those are the phase-specific agents. Agents or drugs that are affecting specific phases in the cell cycle. They are affecting specific phases in the cell cycle. Then we can also have phase non-specific agents. These ones are not affecting any. They are not affecting any specific phase or any specific phase in the cell cycle. And you have the nitrogen master, the cyclophosphamide. When we look at this, we look at the mode of action, the alkylating agents, nitrogen master, cyclophosphamide, chloramucil, camustin, dacarbazine, bisulfan, L-asparaginase. So in other words, L-asparaginase, I think we also mentioned it elsewhere, if I'm not wrong. Did we? We didn't. I think we mentioned it somewhere else. Like we have it. So we have the L-asparaginase, cisplatin, procarbazine, and actinomycin D. So those are phase non-specific. And then we have finally the drugs that are specifically effective against proliferating cells, but they are not phase-specific, but they will affect proliferating cells. Again, you can see you can have one drug being mentioned in different classes because it can be able to act. using different, you can be able to act at the different areas, although it might be using the same mechanism. The mechanism of action is the same, but it can affect the different areas. It can be a cell-specific, it can be non-specific, it can also act as, it can actually act, it can be a non-cell specific, but it is affecting the cells that are proliferating very quickly. So we are saying phase non-specific, you have the nitrogen mustard, we have looked at all those, and you see most of these actually, most of these here, which are phase non-specific, you see most of them are alkylating agents. And then we have the drugs. They might still have some other mechanisms, but most of them, like the nitrogen master, the nitrogen master, cyclophosphamide, most of them are alkylating agents. Drugs that are specifically effective against proliferating cells, but they are not phase specific. Again, you have fluorouracil, and I believe we did mention fluorouracil somewhere else. Can you see it? I did mention fluorouracil. There is nitrogen mustard, cyclophosphamide, chlorambucil, only in one class only, methotrexate, daunorubicil, like it's not anywhere else. Wow. I was thinking like it, I don't know why I was thinking like I'd seen it somewhere else. Cyclophosphamide, that one you have mentioned there, phase non-specific. Dactinomycin. Dactinomycin again is an antibiotic. You haven't mentioned it anywhere else. It is there. Cyclophosphamide, you have mentioned it twice. Fluorouracil, yes, I knew, I could remember we have mentioned it. 5-fluorouracil is also specific, synthesis specific. So it can be able to act at the cells which are dividing very fast in a non-specific way. At the same time, it can also act within the cycle in a very specific way by having an influence on the S phase. So it can act just on the proliferating cell, but it's not specific, it's not cell-specific, or it can act in a phase-specific manner. So these drugs, you look at all of them, so they shouldn't worry you. You look at all of them, and you'll be able to classify them and understand even their structures. So please note that that is one way of classifying the drugs. Classifying the drugs according to whether based on the site of action. I believe this you might do it more in pharmacology. So any look at our classification, I would want us more to stress, to put an emphasis on the chemical classification / mode of action, because indeed they're going hand in hand. Because like now when you say alkylating agents, that is the mode of action. So when you look at the alkylating agents, that is the mode of action. Then now, under the alkylating agents, now you find that you have different classes of drugs which have different structures. So that's why I'm saying it is both structural and also mode of action. So it is a mixed of those two. So the first category, alkylating agents, we're going to look at it in details. But when you see the word alkylating, you can see you are adding an alkyl group. And more often than not, you are adding an alkyl group to the basis of the DNA. But we'll look at that in details. So we're looking at the alkylating agents, and the alkylating agents can be further subdivided into different structural categories or chemical categories. And you can start with the nitrogen masterns. And under the nitrogen masterns, you have different drugs. You have the mecloethamine or mustine hydrochloride. You have the cyclophosphamide. You have the ifosfamide, melphalan, and chlorambucil. So these are just examples that represent the nitrogen masterns. And you can see mecloethamine. I hope it is, the structures are big enough. The structures, and then I'll move it. So if you look at it, you have, this is a nitrogen, the central nitrogen, so that we are calling them nitrogen masterns. So all of them will have a central nitrogen atom, and then you can see the CH2, CH2, Cl3. This is our alkyl group here. So remember they are alkylating. And you can see this here, these chloro groups, remember, electrons, very strong electron withdrawers. And those electron withdrawers can be easily lost as chloride ions. So this is a group which is very important. That group there is very, very important. So you have the macroethamine. But if you look at our cyclophosphamide, you will still see it has the same group. It has that group there, very important group for alkylating. So they will add the ethylene group there. That ethylene group there is what will be added as an alkyl group. Remember, they're alkylating. Ifosfamide, very close. The ifosfamide is very close in structure to cyclophosphamide. But again, you can see the group that we are talking about there. Phosphomide. Then also, sorry. You have the chlorobutane. So again, you can see they still have that group and the nitrogen. So you can see that either you have a disubstitution of the, most of them are chloro, disubstitution of the chloro alkyl group on the nitrogen, or a monosubstitution, either a disubstitution or a monosubstitution on the nitrogen. So you can see in the ifosfamide, it's a monosubstitution. If you look at the cyclophosphamide, it's a disubstitution. You look at the macroethamine, again, it's a disubstitution. If you look at, so again, if you look at the meophalan, it's a disubstitution. In other words, you can't be able to establish a general structure. So you have this group, like for this disubstitution, you can call this group here an R, this one here. The disubstitution, you can call that an R. You can call this a methyl group, that an R. Let's leave that first. We can also call this an R. Look at that. We can also call this an R here. Then you have your disubstitution. So we are saying, therefore, we do have a pharmacophore. These drugs have an important pharmacophore, which they must have for them to bring about the alkylation. We are going to look at the actual mode of action after we look at the classification. So that's the first category. And then we have the ethylene imines. You have the ethylene imines, and under the ethylene imines, you have the thioterpa. And this is the thioterpa where you have these three groups there, and then you have the thio group there. So that is the thioterpa. And then this is triethylene melamine. And if you look at our triethylene melamine, again, there is some similarity. You can see this group there. You can find it there, there, there. We still have three of them. There, there, there. And then, of course, we do have aromatic group containing, which has got 3 nitrogen atoms. And, of course, you find that on each carbon where you do not have the nitrogen is a position where you have our three-membered ring containing a nitrogen. That is where you have it joined, where you do not have a carbon. So again, it is a structure which is easy to remember, because you draw first of all your benzene ring, and you put on every adjacent position, you put a nitrogen, and then on the positions where you do not have a nitrogen, you put your 3-membered ring with a nitrogen, and the nitrogen is the one which is binding the carbon. Then that gives you the triethylene melamine. And therefore, again, quite some structural resemblance there, of course. Here, they are joined to a phosphorus, and one of the substituents is a sulfur. Then again, we have the other structure. Again, a lot of structural resemblance, because you can see we still have this central ring here, which also still has 3 nitrogens. That's our central ring. And now, in place of a cyclic ring, the cyclic ring is opened up. So you break this bond here and you open up the cyclic ring. So that nitrogen you open up, this nitrogen here you open up, this nitrogen then you open up. That's the only difference. So that one you have opened up, the same kind of drug, that one you have opened up, that you've opened up. And when you do that, you get your hexamethyl melamine. So again, the basic structure is indeed the same, with opening of the tricyclic ring to give us that drug. And those are the 3 in that category. Then we move to then, so that those are the 3 in that category. Then we go to the alkyl sulfonate. Alkyl sulfonate, this is the alkyl group there. This is a sulfone. That's why you're calling it an alkyl sulfonate. And under the alkyl sulfonate, we have the bisulfone. And remember, as I have said, these are our alkylating agents. We are now only classifying them according to their structures. But they are all alkylating agents, but they have different structures. But of importance is that all of them will have an alkyl group. Or of importance is that all of them, like this alkyl group here, this CH2, this alkyl group can be donated and can be added. This alkyl group there can be donated and can be added into, remember, that cell. Remember, we are alkylating the DNA, the cell, which is dividing. So once we alkylate it, we stop it from the continuous dividing. We block it from dividing, and therefore we must have that group that we're calling the alkyl group. That must be present. And as we have said, it's a sulfonate. It has that sulfonate methyl. It has a methyl sulfonate derivative. It has that group on both sides, and therefore it is able to give us the alkyl group for that purpose of alkylation. So that is the alkyl sulfonate. And then from there, we have the nitrosoureas. Again, they are still alkylating agents. The only difference, you can see the word nitrosoureas. You can see that group here. They have a nitroso group. If you look at them, there's camustin. You can see that nitro group. You can see that nitro group. You can see this nitro group. So that is what qualifies them to be called the nitroso derivative. So they have the nitro group, and then they are also ureas. In that, if you look at this group here, N, C double bond O, N, that is what you get in ureas. Ureas, urea is usually C double bond O, NH2, NH2. So they are derivatives. They are nitrosourea derivatives, and you can see that structure that is giving us the nitroso group there. And then here, this group here, there, coming up there, coming down there, is a urea group. And if you look at all of them, they will have that group. So when you look at this, C double bond O, God help me. So if you look at this, as this one has a CH2Cl, it also have that alkylating group, the one we saw in the nitrogen mastards, but they are called nitrosoureas because of the unique group. So they have, if you look at that, they have that, then they have that, and that group is joined to the nitrosourea there, nitrosourea. So that this portion already is the same. And then you see the C double bond O, NH. So when you look at camustin and lomustine, the only difference is this. We can call this our R. So this will be our R, because if you look at it, it has Cl, CH2, N. So we are starting Cl, CH2, N double bond O, C double bond O, But you see, when you look at lomustine, it has two of these chloroalkyl groups. That's the difference. That it has lomustine has two chloroalkyl groups on either side. So one side, of course, you have the nitrosourea, the other would be the free side of the urea. And on one of those sides of the urea, it has a chloroalkyl group. And then on the other side, it has also a chloroalkyl group of the nitrosourea. But for the lomustine, so we are therefore saying it is we can be able, because we have to note where this group is joined. This group is joined on this side. So this group is joined on this side. So the one we are considering to be our group is this one, and also this one. So this one is our R group, and that one is our R group. The rest of the structure is the same. So, and again, najaribu tu pole. Then we also have the other drug. We are calling the streptozotocin. And this one again is the same similar structure. We look at this. There is N double bond O, N double bond O. And of course, a slight difference in the arrangement, that in this N double bond O is the external, it's completely the external substituent, unlike in this one whereby the N double bond O, because it's like almost the same, because we have N double bond O, we can consider this to be this one here, and then that N double bond O is joined to a nitrogen just like this. So this methyl group is what is standing for this. Methyl group standing for this group there, this methyl group. And then you have your C double bond O NH, C double bond O NH, and this is what is standing for R. So this one has two different groups. Here is one of the R's joined to a NH just like this. And then instead of the haloalkyl group, it just has a methyl group. Just give me a few minutes. think when I talk is when it versus the cough, but I will be fine. So therefore, you are saying this is one of the other R groups here. And it, of course, the other R will be this one, where this one is a methyl group. But again, we can't see a lot of structural resemblance within the group. Please note, when we talk about the structural classification, the similarities will be within the group. Just as we looked when we were looking at the antibacterial agents, we would say we have the penicillins as one category. The structural resemblance will be within the penicillins. Then you look at the cephalosporins, structural resemblance within the penicillins, cephalosporins. Then you look at another category that like the beta-lactamase inhibitors, and the same thing applies here. It's only that we do have very many categories. So we need to work a little bit harder to remember all of them. So we are saying these are the nitrosoureas. I've explained that's nitroso group there, and then nitroso group there, and then of course you have the urea group there, and that's where the name comes from. And for the first one, we have said we have an R. One of that group can be an R, and that is an R. But for the streptozotocin, of course, it's a nitrosourea. You can see that is a nitroso group, and then of course that is a nitrogen. So it's important to note when you're trying to remember the structure that the nitroso group is attached to the urea. So once you do your N double bond O, the next group, N double bond O, the N double bond O must be attached to the urea. So N double bond O attached to the urea. So once it's attached there, then again this is the urea, and then attached to the R. So that is the other category. Then you have the triazines. The triazines. And when you look at the triazines, I think they are called, but any good reason we call them the triazines, because tri means should have 3 carbon, 3 nitrogens, 1, 2, 3, that has 3. Now, this one has more, 1, 2, has more. This one has also quite a lot. But okay, they call them the triazines. I'll find out the exact reason, and I can promise you. But the first one is easy to know. It's a triazine. It has 1, 2, 3. It has 3 nitrogens. That's a procarbazine. And then the dacarbazine, I think we are talking about the nitrogens being within the side chains. I think that's what they want. The nitrogens being within the side chain. And here we do have 1, 2, 3. In the carbazine, we have, I think this is what they call them the triazines, these 3 nitrogens, because that's an amino group. I think the nitrogens must also be substituted with a hydrocarbon, because you can see this, I think, is what is qualifying the carbazine to be a triazine. You can see that N, that's substituted, and that again, that qualifies it to be a triazine. Let's see whether this other one, how does it qualify? Where is it going now? I think it's this group. This one qualifies again because of this group, because the triazine cannot be part of the aromatic system. If you look at this, not part of the aromatic system. So here, not part of the aromatic system, and here also not part of the aromatic system. We have that one, that one, that one. I hope the fact that it has, even when it has the 3 nitrogens, in the different side chains, but they are 3 nitrogens, not part of an aromatic system. They can be part of an aliphatic system, not part of an aromatic system. And also these 3 nitrogens again here, again not part of an aromatic system, part of an aliphatic system. And even here again, this is what is qualifying them to be the triazines. But of course, when you look at them, the nitrogens do have actually they are part of a very different structure, because if you look at this is an amide, so they are a bit different, but I think they are qualifying them to be triazines because of the 3 nitrogens. So here we have procarbazine. Again, you can see the structures are quite different. We have procarbazine, but all of them, that one has an aromatic system, this one has an aromatic system, and even this one has an aromatic system. So it looks like, and if you look at them also, all of them, the triazines, also have an amide. So all of them, the triazines, all of them, like this, you can see this one has an amide here. And incidentally, I'll check this structure again, because for most of the others, the amide nitrogen is not being counted. But for the procarbazine, the amide nitrogen is part of the triazine. So you can see also they have that amide. You can see this one also has an amide. And you can see also that has an amide. So that is also something else, a carboxyamide. That was carboxyamide, and also a carboxyamide. So all of them do have an amide. So those are some of the structure, because you look for the drug, look for the structural similarities. And some of the structural similarities in these triazines is that, of course, they have at least 3 nitrogens. They do have an aromatic system, and all of them, you can see they have the aromatic system. So that is something you can see in all the structures. And then they have the carboxyamide. All of them have a carboxyamide. So those are some of the structural features that are part of those triazines. But of course, as I have said, we are going to look at them in more details and be able to understand the structure, the SAR that governs these structures. Then the next one, just kindly remember, we are still looking at the alkylating agents, but all these different alkylating agents have different structures. So the others, and again, the classification sometimes differs in different books. Some of the books you might find that they have classified cisplatin within the miscellaneous, but the one I was using classified cisplatin amongst the platinum coordination complexes. And of course, the platinum coordination complexes were also alkylating agents. So what we will do is that I think when you answer my questions, you will answer according to the classification we have studied. Because as I have said, you can have different books classifying differently. So if you use those other classifications, it will be very difficult for us to answer the questions in a similar manner. So kindly just follow the classification we are using, because as I've said very clearly, some books will give you cisplatin as a miscellaneous, and I'm giving cisplatin under platinum coordination complex and under the alkylating agent. So we will look, when we are looking at that category, we will see why we are calling it an alkylating agent. So that is cisplatin. Carboplatin, again, you can still see ammonia. You can see these, you can call them ligands. Ammonia, this nitrogen is fully saturated. It has its the 3 hydrogen substituents, so it can only use its lone pair of electrons. So this is a ligand, that's a ligand, and you can see that is repeated also there. But when you have the oxaliplatin, the oxaliplatin is a little bit different. Oxaliplatin is a little bit different, but you can still see it still has its the platinum there. And then it has, of course, but this ammonia here now has 2 substituent, and then of course it has this other substituent on this side. So, but you can see this ammonia having, under normal circumstances, this ammonia will have only 1 substituent. Here, this would be 1 hydrogen, because this is another one, that is another one, and yet it's not carrying a positive charge. Because it's coming in almost like a ligand. So again, so there is still similarity, because this we can say is representing this and this. It's only that one of these hydrogens here has been replaced one of these hydrogen here has bonded a cyclohexane ring with retention of activity. So even when we look at oxaliplatin, there is still structural similarity because that platinum, that NH3, that NH2, NH2. So that is similarity from this side. So of course, if you leave, first of all, leave this group, but if you look at that, this was like the NH3, and this was NH3 in cisplatin, and then the platinum, and then of course the halogen group now has been replaced with this group, but you can still see that there is structural similarity that allows for those drugs to still belong to the same class. I need to do at least a minimum of 30 slides. Then, of course, after that, we do have the antimetabolites. So again, so we have now moved from the first category, which was alkylating agent, and having several classes of structurally different compounds which are classified as alkylating agents. And then the second category is the antimetabolites. And I hope you do understand what antimetabolites are. Antimetabolites are compounds that can be taken up by enzymes or taken up in metabolic processes, but they will not be able to bring about the same process that is brought by the metabolite, and therefore they will block. So those are the ones we call antimetabolites. These are compounds that are structural analogs of the substrate within the body. They are structural analogs of the substrate in the body, and therefore are readily taken up by the enzyme. The enzyme mistakes the antimetabolite and the substrate because they have a lot of structural similarity. And once the antimetabolite is taken up, because it has structural differences with the metabolite, when it is taken up, it blocks the process. And therefore, unity cell division, it will block the cell division, and therefore the cell division will not go on. And under the antimetabolites, again, we have different classes. We do have those which, and then most of the antimetabolites are mainly derivatives of the bases. You know, within the DNA, we have bases, we have the pyrimidine bases, we have also the purine bases. Most of the metabolites have, of course, there are also other different ones, but most of them are structural analogs of the pyrimidine bases and the purine bases. Of course, we also have the folic acid antimetabolites. So you have the pyrimidine analogs, and you have the 5-fluorouracil, which you have mentioned severally. You have the cytarabine, which is a cytosine arabinoside. You have the capecitabine and gemcitabine. Again, that is, you can actually look at this and draw the structures. That is a 5-fluorouracil, and you can, it already has the name uracil. It is a pyrimidine. This is a pyrimidine. Uracil is a pyrimidine, and we are calling it 5-fluorouracil because, you know, uracil has a methyl group there in place of a hydrogen. So now, in place of the methyl group, you have a fluorine. That's why we are calling it 5-fluorouracil. That structure, that's what's found in uracil and a methyl group. This is floxuridine. If you look at floxuridine, again, this is what we are looking at. This is just the sugar. So again, this is a pyrimidine, the oxygen there. Then it is still the fluorouracil, but this sugar, this time, it is attached to a ribose sugar. So indeed, it's a nucleoside. It is a nucleoside because it doesn't have a phosphate to make it a nucleotide. So that is a base. That's a nucleoside. If it has an addition of a phosphate, then it becomes a nucleotide. So there, again, if you look at this is very similar to that. The only thing that has been added is a sugar. But this ribose sugar, please note also, at position, you look at it, this is position number 1. At position number 2, the RNA will have an hydroxyl group there. The deoxyribonucleotide or the ribonucleoside will have no hydroxyl group. So this is a derivative of a deoxyribonucleoside without a hydroxyl group there. But again, very similar Again, you can't see, as I have said, it is a pyrimidine derivative, just like for uracil. And then after that, you have again capecitabine, again the same. The same structure, but now at position number 1 here, where you see here we have an oxygen, here we have an amino group. I think when we have an amino group, that is we have the uracil, we have under the pyrimidines, we have uracil. Which other one do we have? We have uracil. Which other one do we have? Thymine and cytosine, isn't it? We together? Let's look at them so that we remind ourselves. Always make sure I have them somewhere. I should have them somewhere. Just about to finish because of those few minutes I wasted there. Yeah, here we have them. I always make sure I have them. So if you look at thymine is the one which has a methyl group. We have cytosine. Cytosine is the one which has an amino group there, and an oxo group between the nitrogen. So you have it has an amino group there and an oxo group. Uracil is the one which has both oxo groups. So uracil, the only difference between uracil and thymine is that thymine, this is position 6. Thymine, that's position 6, that's position 1, 2, 3, 4, 5. It's usually easier to talk about the position. So when you talk about thymine, at position 5, because when you start, this is position 6 always. So that's position 1, position 2, position 3, position 4. At position 5, and that's why we are calling it 5-fluorouracil. At position 5, thymine has a methyl group. When you look at cytosine, at position 6, because this is position 6, position 1, position 2, position 3, position 4, position 5. For cytosine, at position 6, in place of one of the oxo groups, it has an amino group. For uracil, of course, at position number 5, it has a hydrogen. That's why we are saying, if you look at the other drug which we are looking at, this position 6 has an amino group. So that's why I was saying it is cytosine, because of the presence of the amino group. Because uracil and thymine are usually similar with a difference of a methyl group at position number 5. So that's what I wanted as. I always make sure I have those things so that in case we want to confirm, sometimes we don't remember all these things. Want to confirm, we can't be able to confirm easily. So if you look at the drug we were looking at, here, again, here we have, let's see, this is position 6, this is position 5. So position 6, position 5, this is position 1, 2, 3, 4, 5, 6. So this position 6, it has an amino group, so that's cytosine. So this is a derivative of cytosine, and you can see here at position number 1, 6, 1, 2, it has the oxocin. So this is a derivative. So capecitabine is a derivative of cytosine arabinocyte. So you can see because it has a sugar, but of course the sugar is also a bit different, because for the normal sugar for the DNA, this group here is a CH2OH. That group is what we usually have. So again, there is structural similarity. Remember, they're calling them antimetabolites. So they would not have the proper structure of the metabolites. Otherwise, they will be taken up and the normal processes will go on. So there will be slight structural modification so that they do not allow, when taken up, they block or they result in formation of fraudulent product. Again, if you see this, again, very similar. That is thymine, and this time you can see these two groups here on the sugar are deoxy. Those two groups, again, that makes a lot of difference. And then you have gemcitabine, a very, very important drug. Again, you can see here at that position there, position 2, you have two fluoro groups. The other structure is almost very similar. Again, this is cytosine. If you look at this cytarabine, again, cytosine there. And again, you can see that has an amino group, CH2OH, OH. The difference here, I think, is the positioning of the hydroxyl group. This positioning of the hydroxyl group is what is different. The orientation of this hydroxyl group is what is supposed to be different. It is supposed to be vertical. So, and in the normal sugar, in the ribose sugar, it is supposed to be vertical like this. But in the cytarabine, basically everything is the same. But this sugar takes a horizontal orientation. I think we did about vertical and horizontal orientations when we were looking at gentamicin. Remember gentamicin, the fourth carbon, where we said it is tertiary. You have to remember those things. I think we said it was tertiary and in a vertical, and that changes. The fact that this orientation is different, instead of it being vertical, like in all the expected ribose sugar that is found in the DNAs, the fact that it is carrying a horizontal orientation makes all the difference, and that becomes an anti-metabolite. Then you have the 5-azacitidine. In the 5-azacitidine, again, we can look at the difference is very clear. Instead of it having 2 nitrogen, it has 3 nitrogen. Again, makes a major difference. Everything else is the same. And then there is the decitabine. Again, instead of the 2 nitrogens, it has the 3 nitrogens, and a slight difference from 5-azacitidine in that this is a deoxy carbon. So when you look at these structures, they're able to show you the structures very similar to the substrate. This has, remember, when the DNA, for you to form the DNA, you must have the substrates, and the substrates are the nucleotides. The nucleotides will have a base, they will have a sugar, so the sugar and 2 phosphates. So when this group is added on a sugar, it's usually added on a sugar and phosphate, it will receive the enzyme that is responsible for synthesis of the DNA. So normally, these molecules are inactive. They usually need to be changed to the nucleotide for them to have activity. Now, when they are changed to the nucleotide, the enzyme responsible for the synthesis of the DNA is not able to differentiate this when these substrates are part, or when these substrates are formed into the nucleotides. They are not able to differentiate the antimetabolites when phosphorated, and they have a sugar and the actual substrate. And the minute they pick this, when it has a sugar and it is phosphorated, it will stop. It will stop the DNA synthesis from going on, or it can be incorporated. And once it is incorporated, it will bring about the formation of a fraudulent DNA, which cannot bring about the expected processes. So I hope that is clear. That's obvious. So when we look at these structures, we should be able to establish what the differences are. The other one will be purine analogs. Again, if you go and look at them, please do look at them because of the time. So we can look at 6-mercaptopurine. 6-mercaptopurine. So you can see this is a purine. A purine is a bicyclic ring. So if you look at the 6-mercaptopurine, you can see at position 6, it has an SH group, and that's why we are calling it mercaptopurine. Thioguanine. So this is now guanine. So when you have guanine, it's have a double bond here. So now when it becomes thioguanine, in place of the keto group there, you have an SH. So if you go and look at all the drugs, because we have now the time until the next lesson, look at the current drug, the mercaptopurine, the thioguanine, the azathioprine, the fludarabine, cladribine, and pentostatin. Please write them down, look at them, and compare them with their substrate with the substrate that they are imitating. You look at them, compare them with the substrate that they are imitating, and you will be able to see that there is a very slight difference somewhere, and there's the enzyme responsible for picking that substrate is not able to differentiate the antimetabolite and the substrate. It picks up, when it picks up the antimetabolite, the whole process is stopped. And once the process is stopped, then the DNA synthesis is stopped. Remember, these cells, not microorganisms, but these cells are dividing very fast. They require a lot of DNA. So once the DNA synthesis, remember we said there must be replication of the DNA. So for this other new cell. So once the replication of the DNA is stopped because you have introduced a strange molecule, once you stop the replication of the DNA, then the multiplication or the division of that cell will stop. Once the division of the cell stops, then for sure you will stop the cancer. Now the problem is that the enzyme within the normal cell can also pick these drugs, can also pick these antimetabolites. And once it picks the antimetabolites, the cell division within the normal cell will also stop. And the reason for the various toxic effects that we did observe. I think we have done at least that slides. I'm having a bit of a challenge with whenever I get these colds, they severely affect my speech and my ability to talk. But we will try even tomorrow. I hope it will have cleared a bit. When I get this, my doctors advise me not to talk. But how do you teach without talking? It is impossible. So I'm sorry for the disturbance of the inconvenience, but diseases, nobody is a hero to a disease. So I hope you have learned something. You have started with the basics of cancer. And once you understand the basics of cancer, you will also be able to understand the drugs that are used in the management of cancer. Do we have any questions? Any questions, my dear students? Thank you. Thank you for those who have said